Welcome guys, welcome back. So today we're going to talk about generalized linear models. What are those? What are general linear models? While they're a family of models that try to learn the variable you want to predict in a way that linearizes or makes some linear divisions within the data you provide that maps to the values that you're trying to predict. Now, what does that even mean? A lot of these are going to stem from concepts that are age-old that we've all have heard of before potentially, and that we're going to review today. Now, before we continue, please subscribe to the channel and then like the video. The general linear models is a family of linear models. So we'll start with our very first one, and that's going to be the ordinary least squares model. Now, this one in particular is actually something we've all dealt with in high school or college if you took statistics. It's also called the best fit line. Now, even after I said that, and you still haven't heard of it at all, maybe it's time to pick up a book and start reading a little bit. But ordinary least squares models, or the OLS model, essentially tries to take in the sum of your columns in your data, assign a weight to each of those columns, and then takes that weight, multiplied by those columns, and then sums them all together, and then adds some constant value at the end of it all, and that should be your predicted values. Now, there's other variations of this, which we'll talk about and describe later on in the video, but this is actually the very first model that data scientists typically gravitate towards. And that's because of how easy it is, how easily explainable it is, and it's something that we've, at least for data scientists, we've actually have seen this numerous times in our studies. And so this is something in particular that is kind of like one of those baseline tools that you need to have in your pocket, so to speak, or toolbox that you need to actually utilize. Now, this isn't the only. We mentioned ordinary least squares. There's actually other variations of this too. Because of the least squares model and how sensitive it is to the coefficients in or rather to the columns in your data, it actually can create a model that may not actually generalize well to the data that you have. And that's because maybe you have some columns that actually aren't needed. Maybe they're just empty noise. And that noise is going to really confuse the model, and it's going to make it difficult for it to actually learn the weights to apply onto the columns to sum up to equal to the data set. And so how do you handle that? How do you deal with that? Well, there's two types of variations of the ordinary least squares model. This is called the ridge regression model, which essentially, geometrically speaking, it goes and takes the coefficients, all the coefficients of your model, and tries to force them in some type of almost some type of square. I mean, not square, rather circle of a certain radius. And so this geometric, it might be a high-level concept. If you want to learn more about ridge regression, just Google it. But essentially, ridge regression, what it seeks to do is it seeks to enable each of the coefficients of the model to still play a part, but because it's going to force the coefficients to be kind of like a point in a circle, it's going to kind of flatten some of them, not to zero, but to a very low value, and try to tame everything. So it's not going to force things to zero, but it's definitely going to try to balance, everything out. Then we have lasso regression. It's another variant of ordinary least regression. Lasso regression is kind of like the same concept as ridge, except you're putting everything in a square. And so what happens now is this actually allows some of the coefficients to equal zero, and that actually forces some columns to not even be turned on at all, so to speak, when it comes towards predicting the values. And while that can be useful, it sometimes doesn't give you the best results, and that's just inherent due to the fact that you're dropping data. Because even though that data may not have some noise, maybe have a lot of outliers, there actually may actually be something there that can be useful. So you may not want to actually throw it out, but you may rather just kind of reduce, so to speak, the influence of that noise. And that's for some cases. Other cases, you actually might have something you want to throw out altogether. And so that it really depends on your data. And so this is where the last variant that we're going to talk about of the ordinary least squares model is the elastic net model. Elastic net is essentially the combination of ridge and lasso. And so this allows your model to essentially, depending on the weights you define, because you actually have to set a couple of additional parameters in your model, but essentially depending on some things that you define yourself, you're actually able to kind of control how much of the comps you can kind of throw out and how much you should keep, but then also control how much variance should, or rather how much the weight should fluctuate, kind of speaking as circles. So depending on the coefficient, you can either make the circle very large, and the coefficients can be anywhere in that range, or it could be much smaller, and then it forces your coefficients to kind of be in that, that smaller circle of that larger circle. And so that's kind of that's the variant, and there's other variants too, which we'll talk about, but we're going to actually classify those as a different type of model just because of the inherent, because these techniques I just described, because these are techniques: ridge regression, lasso regression, elastic net regression. Each of these are really just variants of the linear regression model, and you actually can apply these same concepts to other linear models in the family depending on the coefficients. So it's not really something that is special to linear regression. So I'm going to talk about how each, I'm going to talk about other models with the assumption that we just went over ridge, lasso, and elastic, and these three are kind of techniques or variants you add on to the parent model. So we just finished talking about ordinary least regressions with the three variants. Now the next model really for us to kind of consider and talk about is going to be logistic regression. Now, logistic regression is actually kind of like number two. So ridge regression, linear regression is predicting real values. Essentially, these are predicting values such as the price of a house, predicting maybe what's the next stock price is going to be. Logistic regression is designed for classification, and this is when you have categorical values. Now, these categorical values can be binary, could be 0, 1, or it could actually range from a number of categories, such as predicting whether this image is a dog, a cat, or a frog. And you have those three choices, and you can use logistic regression to help you predict whether your category is going to be dog depending on the data it sees. So the main difference between logistic regression and linear regression is actually, besides the classification part, is essentially what's called a loss function, so to speak. I'm not going to go into that in this particular video. We will talk a little bit more in depth about loss functions in another video. But for now, just bear with me. So essentially, the difference between logistic regression and linear regression is this function that actually defines how close you are to predicting the right value. And that's what loss function is. The loss function is essentially a function that helps the model understand how close it is to predicting the right value. And depending on the type of loss function, lower is better or higher is better. We're going to assume lower is better in both cases. And so for linear and also for logistic. Logistic regression uses a function called log loss. Now what's that? Well, the log loss function more or less is just going to be the log of your probability that you're, say, let's assume we're doing binary classification, so we're predicting zeros and ones. The log of the probability that you're 1 times your 1 plus, well, 0, or rather 1 minus, 0, times the probability that you are 0. And so that's the formulation, so to speak. You sum all those up and you take the average. Potentially you can if you want to, you don't need to, not all the time at least. You sum all these up and you try to make sure this is as small as possible. This is by definition the log loss function, and this is by definition how you actually tell the logistic regression model you're close to the predictions. Now I mentioned probability. So probability is essentially going to be some type of weird formula. If you have any more questions, let me know. But essentially it's just going to be, and this is depending on the textbook, you can do 1 over 1 plus the exponential. So again, if you're familiar with math, it's going to be the coefficient e, so the exponential e, so it's going to be 1 over 1 plus e to the a being your data matrix, times w being your weights. Again, remember, this is based off of a linear model. So those weights relate back to kind of a similar concept for linear regression. Plus some b, which is going to be your coefficient, your constant values. And so you can use that formula to define your probabilities, or 1 minus that. Either or, depending on how you look at it. Some people use the latter, 1 minus 1 over 1 plus e to the aw plus b. Some people use that. That depends on how you feel. But essentially, these are the this is the way to calculate the probabilities for a logistic regression. Logistic regression is, has other variants too, like the ridge, lasso, and elastic. These are kind of your 3 variants, and this is for the same reasons as for linear. This is just to provide some more variation, protect yourself against random noise in your data. But essentially, those are the 3 variants that you can also apply to logistic regression. So, logistic regression and linear regression, as I was trying to get to before, are both 2 linear models, and each of these linear models are extremely helpful and extremely useful for predictions overall. Now, there's other types of linear models too, which we won't go into detail here, but I am going to tell you one more model that actually is extremely useful. That's for linear regression, and it's Huber linear regression, Huber loss. Now, Huber linear regression has the same type of prediction variable or predictor function, so to speak, for the linear regression, where it's just your data matrix A times your weights, the weight vector, plus some B, and that would be your constant coefficients. And that's kind of like how you do the predictions. But how you do the loss function, you're no longer using the ordinary least squares model. You're no longer using the ordinary least squares method. You're actually now using a kind of a weird mesh, if you can think of it like that. Essentially, you're going to be taking the difference between what you're predicting versus what you're trying to predict. Basically, your predictions and the actual values. Take that difference, take the absolute value, and you're going to try to see if it's above or below a certain threshold. If it's below, say, a certain threshold, let's say mu or u, if you're not familiar with Greek, then it's going to be squared. You square that difference, and that's going to be the value you choose. Well, half squared that difference. Otherwise, if it's more than that u, you actually just take the absolute value of it and divide that by 2. So you see here, you use a linear type difference if you're above a threshold, and then use a square difference if you're below a threshold. And what that's going to do is actually going to protect you against outliers in the y variable, because there's outliers in y variables as well. And the y variables I'm referring to is the variables you're trying to predict, so the actual values. Sometimes you actually have outliers in your actual values along with the data you're provided. You're just given outliers everywhere. So now you still want to learn from it, because maybe those outliers may not actually be outliers by themselves. Maybe what you think are outliers in training data from your A matrix may actually correspond to what you think would be outliers in your Y variables. You kind of need to keep the outliers, so instead of removing outliers, it sometimes might be best just to limit their influence. And that's what the Huber linear regression model is doing. It's limiting the influence of the outliers, so that way your model doesn't allow the weights to be affected in a huge way by those outliers. And so that is another linear model that you can choose. And then, as I said before, you can add on the other variants. So you can add on ridge regression, lasso, and elastic net. You can add these 3 variants onto this model as well. So these are 3 models, more or less, we use within data science: linear regression, logistic regression, and Huber regression. And then we have those 3 variants of ridge, lasso, and elastic. There are more models that are in the linear family. The Poseidon, Bernoulli. You have also binomial regressions as well. And these are more statistical type models, but you actually can still use them, and their distributions do come up. You also have log normal data, so that kind of forces you, even if the data has a linear division, because of distribution, your typical linear model won't be able to detect it. And so you have, these are the other types of linear models that are in the family that we're not going to talk about, mostly because we don't use them in data science frequently. The distributions are there, but the actual models themselves are not. They're not used. So, it is what it is. What can you do? So, hopefully you enjoyed this video. Again, as a recap, we went over linear regression, logistic regression, and Huber regression, along with the 3 variants with ridge, lasso, and elastic. And remember, ridge regression does a circle, lasso does a square, and elastic is a combination of both of those. So I hope you enjoy the video. Please subscribe to the channel. As a reminder, subscribe to the channel and like the video, and comment. Tell me what you think. Tell me what you think about the material. All right. Later.